So the next very interesting problem is called the subset sum problem, which also can be solved using dynamic programming, right? So first understand what this problem is. Imagine if I'm given a set of numbers, okay, a set given in, let's say, an array, right? So let's assume I have a set of numbers which are, let's say, 3, 34, 4, 12, 5 and 2. And let's assume all these numbers are non-negative numbers or non-negative integers. Let's just say they're non-negative integers, just for simplicity. Okay. And let's assume I'm also given a variable called sum, which is also an integer, again a non-negative integer, let's say 9. Okay. So this set contains, this is item 1, this is item 2, item 3, 4, 5 and 6. Okay. So these are the items in the set. Okay. And the sum given to me is 9. Now what I want, so this is the input, right? All this is the input, right? What I want to find is, the question that I'm trying to ask here is, are there items in the set? Are there items in the set? Are there items in the set such that their sum is equal to the variable sum which is equal to 9. So for example, if you look at this set, okay, if you look at this set, there are actually two items, 4 and 5. If I sum up both of them, I will get the sum that I'm looking for. Or if I add this, okay. So are there items in the set such that their sum is equal to the variable sum that is given to me? So what we want to find is a true or false answer to this question. Okay. So this is a very simple problem. This is called the subset sum problem because now there is a subset. This is a subset of the larger set, right? This subset has a sum. So if I sum up these two, 4 plus 5, I get the variable sum, which is equal to 9. So there exists a subset whose sum of values is equal to the variable sum. And I want to determine if there are items, or if there is a subset, to be more precise, if there is a subset like this, such that the sum of all the items in the subset is equal to the variable sum. That's the task that we want to achieve. Okay. So now to achieve this task, just like in any dynamic programming problem, again, before we even go into dynamic programming, what is the brute force way of solving it? What is the brute force approach of solving it? If I don't want to apply dynamic programming or anything like that, what is the brute force approach that I can apply? Imagine if I'm given a set of n numbers, right? Imagine if I'm given a set of n numbers and a variable called sum, right? What can I do? I can actually take these set of n numbers. I can create all the possible subsets. Okay. What is the number of subsets of this set of n numbers? The number of subsets is 2 power n. Because given any element here, it can either be present or absent, right? Given any set of n numbers, right? If I'm constructing a subset using this set of n numbers, there are two possibilities. Given a number, it can either be present or absent. There are only two possibilities, right? So the total number of subsets for a set of n numbers is 2 power n. Right? So the simple brute force solution is, let's generate all the subsets. Let's generate all the subsets, right? Let's generate all the subsets and find out, and actually explicitly determine or find out if there exists a subset whose sum is equal to my variable sum, right? Brute force approach of doing it. Okay. But to generate 2 power n subsets, I would need order of 2 power n time, right? To generate 2 power n subsets, I need 2 power n time, obviously, right? So this brute force approach is exponential time complexity. It is exponential in n. That's important to remember. It's exponential in n. Look at this. This time complexity is independent of the value of sum. It's independent of whatever the value of sum is. Sum could be extremely large, but doesn't matter. So the brute force approach has a time complexity of order of 2 power n. Right? or it's exponential in n. Okay, this is important to remember. Now, if I don't want to do the brute force approach, if I want to do the recursion approach, okay, let's write the recursion approach so that once I have recursion, or right, once I have recursion, right, I can obviously solve it, or once I have the optimal substructure, to be precise. Okay, recursion basically indicates optimal substructure here, right? In this case, right, if I can break a problem of size n into smaller problems, I have the optimal substructure. Okay, so my recursion here, if I can write it as recursion, and if I can do some form of intermediate storage like memoization or tabulation, right, then I can obviously convert it into a dynamic programming problem. Okay, so let's actually write it down. Let's say my recursion is S, which means subset sum with n items and sum as my as what I want to achieve. Okay, so this returns true or false. So this function, okay, let's write the cases, right? This function will return false. Let's write the base cases first. It returns false if n equals to 0, which means I don't have any items in my subset, and sum is greater than 0. Okay, if I don't have any items in my set, but the sum given to me is greater than 0, then of course I cannot satisfy whatever I pick, because I don't have any items to pick. I can never satisfy this requirement that the sum of items that I pick is greater than 0. So in this case, I'll always return false. This is the base case. There is another base case, which is if sum equals to 0. If sum equals to 0, I don't have anything to satisfy. Then I'll obviously return true, right? Then, so these two are the base cases. These two are the base or boundary cases. Okay, these two are the base cases. Now there is a third case, which is very interesting. So now the third case says the subset sum with n items in the set and with sum is equal to the subset sum that I can obtain using n minus 1 items, right? If I can obtain this sum, using just the n minus 1 items, skipping the nth item. Okay, if this is true, then obviously this is going to be true, right? If this is one possibility, or this is logical, or if I can obtain the sum value by using n. So there are two possibilities, right? Okay, let me just write it down so that I can explain this to you. Sum minus the set of n. Okay, let me just explain this step by step. So I hope the false and true cases are clear. Now there are two other possibilities here. In this case, I am not using n. So not using the nth item. In this case, I am not using the nth item in my set. In this case, I am using the nth item. I am using the nth item as part of my summation. Okay, if I am not using the nth item, which means if I can produce this sum with some subset of the n minus 1 items, I am good. Or I got to produce this, or if I use the nth item, the total sum will reduce. This is just like the knapsack case, right? If you think about it, right? If I'm picking the nth item, here, this becomes sum minus, I'm already picking the nth item, right? So the total sum that I need to satisfy now will reduce by whatever is the value of the nth item in the set. Because I'm using the nth item. Because I'm using the nth item, the sum will now reduce, right? So here I'm using the nth item, or I'm picking the nth item, and I'm saying whatever is the remaining sum that I need to satisfy, if I can satisfy using a subset of n minus 1 elements. Okay, so this is the recurrence relation. Okay, and this is the crux of the whole story. Okay, so this shows optimal substructure. Okay, very simple. Again, because I'm taking a problem of size n and sum, and I'm reducing it to a problem which is of smaller size, because here I have n minus 1, or here I have n minus 1, and also the sum is reducing here. Okay, so this is the optimal substructure formulation here. These two are the base cases, and this is the recursion case. Right? I hope this is clear. Again, just like the way we have seen other examples, right? For 0-1 knapsack, and for LCS, we have seen the tabular examples, right? we can construct a very similar tabular example using this recurrence relation or using this recursion formulation, right? Now once I have optimal substructure, let's see if I have overlapping subproblems. Okay, if I have overlapping subproblems. Okay, so let's just see that quickly. Okay, so now imagine if I have a problem which is of size n comma sum, right? So this will be broken down into n minus 1 comma sum. Look at this. Look at the recurrence relation. N minus 1 comma sum, or if n equals to 0, sum is greater than 0. So these two are the base cases. Let's just look at these two and have to compute the logical OR of both. If this is true or this is true, it will be true, right? At least one of them has to be true for us to return true. If both of them are false, we will return false. So in the worst case, we have to evaluate both, right? In the worst case, we have to evaluate both, because if this is false, I have to evaluate this to return false, right? So n minus 1 comma sum and n minus 1 comma sum minus set n, right? I'll keep going on like this. Okay, based on the values in set n and based on the numerical value of sum. Okay, based on these exact numerical values. Okay, if I take a specific value for sum and specific values for set n, you will observe overlapping subproblems. You will observe that. Okay, and there can be some cases. Remember, there can be. This is important. There may be some cases. There may be some cases wherein for values of sum and set n have been so chosen. See, we have these two-way inputs, right? I have sum and I have set. Okay, if somebody has chosen these values such that there is no overlapping subproblem at all. Okay, there may be cases where there is no overlapping subproblem. If somebody has chosen it like that, okay, there is no overlapping subproblem. In such a case, what happens to DP? This is a very important question, because this dynamic programming depends on the numerical value of sum and the values that are given in my set. If somebody has chosen these in such a way that there is no overlapping subproblem, they chose these very smartly. Okay, then what happens to DP? Then DP will become equal to simple recursion. That's all. That's all there is. Okay. Now, okay. So this is what it is, right? So this is an important observation for whole of DP, not just this case. Okay. If there is a case where you are not finding overlapping subproblem, then because then I am not storing and reusing anything in a nutshell. Then dynamic programming simply becomes equal to your simple recursion problem. Okay. So now for this whole problem, there are a couple of very interesting cases. Okay. So let's assume I solve it using this recurrence relation. Okay. Let's assume I solve it using this recurrence relation, and there is also overlapping subproblem. Okay. What is one way to write this program? Okay. What is one way to write it? I can write a dynamic programming problem, right? I can write it with order of n into sum. Okay, I can write it with this complexity. And how do I write it? I'll basically create a table. Okay, look at this. If somebody gives me the value of sum, let's assume somebody gives me the value of sum itself. Okay, so where is the recurrence? Okay, here is the reconciliation. If somebody gives me the numerical value of sum and the values of the set, right? I can solve this problem. In order of n into sum by simply doing this. By writing a for loop for I equals to 1 to n, right? And for s equal to 1 to sum, because sum is also an integer, remember. Okay. Here, now I'll start computing. I'll start computing s of I comma s. I'll keep computing this, right? So because I can write s of n comma sum in terms of s of n minus 1 comma sum, and if I compute s comma s n minus 1 comma sum minus the set of n. So I'll keep computing this recursively. Okay, I'll just use the recursion here. I'll use the recursive formula here. I'll use the recursive formula here. So I'll start with I equals to 1, or I'll start with 0 itself, right? I'll start with I equals to 0, S equals to 0. Okay. I equals to 0 basically means I don't have any item in the set. S equals to 0 means my sum equals to 0. So I'll basically start a twin for loop here, and I'll start computing S, I and S. Let's call this small s. I'll keep computing this recursively up to the time I get S, because this loop runs from 0 to n. This loop runs from 0 to sum. And I'll create a matrix. To store all of this, I'll create a matrix called capital S. Okay. Or let's call it capital S. Let's call it table. I'll create a matrix or a two-dimensional array called table of size n plus 1, comma, sum plus 1. Okay. I'll simply store all of these temporary values here. Right. Whatever I'm computing here, I'll tabulate the data in this table. The algorithm is very simple. Okay. This algorithm is very simple. I just loop from I equals to 0 to n and S equals to 0 to sum, and I'll compute SIS using the recursive formula. Okay. And of course, I'll use this two-dimensional array to do that. So what is the total time complexity of this? Because this loop runs order of n times and this loop runs order of sum times, the total dynamic programming itself will run n into sum. The catch here is this dynamic programming complexity is not represented using just n. So what if? Okay, so let's see what happened with brute force. Okay, let's actually see this. Why that is concerning. What happened to our brute force? Okay, what was our brute force time complexity? Brute force time complexity was order of 2n, right? Brute force time complexity was order of 2n. Now, just to generate the sets, okay. Now, if I use dynamic programming, we showed that we can get it in order of n into w. Now, what if? Sorry, no, not n into w. N into sum. Sorry, n into sum. Okay. Now, what if my sum is equal to 2 power n? Because sum can be any large value, right? Then my dynamic programming is going to take worse time than my brute force, right? Because sum can be any large number. If sum is equal to this, then my dynamic programming is worse. My dynamic programming is worse than my simple brute force, right? It's worse than my simple brute force. So it's always advantageous to represent the time complexity using just n. Using just n, which is the size of my set. If I can somehow represent the time complexity using just n, because sum can be any large number. It could even be infinity, right? So if there is any strategy for us to just use n, whatever algorithm you design, the time complexity of this problem of subset sum, the time complexity of subset sum problem is order of 2 power n. If I have to only represent with using just n, right? I cannot reduce any further than the exponential time complexity. This falls in a special class of algorithms. We will learn some classes of algorithms called complexity classes later in this course, right? The very last chapter is called complexity classes, where we'll revisit this subset sum problem and show that it belongs to a specific complexity class wherein we don't know if we can reduce it today. We actually don't have the best algorithm, or to put it other way, the best algorithm we have to solve this problem today, as of today, is order of 2 power n. Okay. So this dp, if you notice this dp right now is polynomial. It is not polynomial in n. It is polynomial in n and sum. Okay. Such algorithms are called as pseudo polynomial. Such algorithms are called pseudo polynomial time complexity algorithms. Okay, so they are pseudo polynomial because while they seem polynomial, right? Because there's a multiplication of two terms. While this seems polynomial in n and sum, if the sum itself is so large, if sum equals to 2 power n, this becomes pseudo basically means false, right? In English, pseudo basically means false. So if sum itself is very large, this whole time complexity becomes as worse as brute force, right? See, look at the brute force. The brute force algorithm does not care about what the value of sum is. right? It only cares about the number of items that I have in my subset, or number of items that are there in my set, not in the subset, right? So this algorithm, the subset sum algorithm, it's a very popular algorithm in study of complexity classes. Whatever recursion I use, whatever DP I use, I cannot reduce it to something that is, in the worst case, remember, in the worst case, I cannot perform better than order of 2 power n. Because in the worst case, my sum can be very, very large number. It can be greater than 2 power n also, right? It can be n power n for all you know. Okay. So in the worst case, you cannot guarantee that the subset sum will work better than order of 2 power n. Of course, if sum is a small number, then order of n into sum still makes a lot of sense. This is still a very sensible time complexity. But in the worst case, whether you use DP, simple recursion, whatever, you might end up with brute force being a better solution because it is independent of sum. So when you actually solve this problem in the real world, right, if sum is significantly less than 2 power n, right, you use the DP based solution. If sum is approximately equal to 2 power n, then it's better off to use the brute force solution, right? So this is the choice that we often make. Right? This is a very interesting problem. This is the reason we are studying subset sum is, while we can solve this problem using recursion and DP, we cannot guarantee that DP will improve the complexity of the solution. We cannot guarantee that. We cannot guarantee DP is better. We cannot guarantee that DP is better than brute force. DP is better than brute force algorithm in the worst case. In the worst case. That's why this is a very important and interesting case in dynamic programming algorithms. While dynamic programming is fun for this, you cannot theoretically guarantee that in the worst case you are better off than simply using brute force, which is creating all the possible 2 power n subsets. Okay, so I hope your appreciation of DP now is getting deeper and deeper and much better.